we're going to cover the following topics. So I'm going to give you a little bit of a background about DNP and SCADA communications. We'll talk about how DNP was developed, the levels of implementation at this point and forward. From levels of implementation forward, we're going to be actually talking about the protocol, DNP message structure, data structure and applications, and then the demonstration. So launching right into it, the origin of DNP, you're tempted almost to say, in the beginning, God created the heavens and the earth. In the beginning, there was no agreement between utilities and vendors about SCADA communications, about how electronic communications would be conducted in a substation. So from one utility to another, different protocols were used. From one SCADA vendor to another, different protocols were used. Frankly, in the 70s, 80s, and into the early 90s, many of the SCADA vendors viewed proprietary protocols. They would sell them as they're proprietary, therefore I can give you advantages that my competition can't do. But they would also, because SCADA systems were very expensive, they would lock in future purchases of their equipment by having a proprietary protocol that wasn't compatible with other equipment. So it was a double-edged sword. And of course, the big contribution that this move to standardized communications in substations provided was standardization, that you could go to different vendors to get intercompatible devices, and this is what DNP really brings us. So DNP was originally developed by arguably one of the leading, best respected SCADA vendors in the 80s going into the early 90s, a company called Westronics based in Calgary, Canada. Through a course of mergers and acquisitions, they were bought, renamed Harris. You hear sometimes the Harris D20, which is their RTU, which ultimately became GE Energy Management System. So this is all a continuous progression from the original company who basically invented DNP protocol. DNP, in case anybody's still wondering at this point, stands for Distributed Network Protocol. The acronym really means anything to distinguish it from other protocols, but no point throwing around acronyms without defining what they mean. It was released into the public domain as a standard. This was contrary to the prevailing commercial practice at the time of keeping proprietary protocols. Westronics believed that there was more to be gained from the standardization than there was from the exclusivity of selling a proprietary protocol, so they moved their proprietary DNP into the public domain. The way that's usually done is by establishing a users group, which has people who have a vested interest in basically the open architecture of protocol, which would consist of not only vendors but also electric utility users who have SCADA systems and are heavily invested in it. This user group would get together periodically and hash out any disagreements that may arise from practical problems that come up during the implementation experience of deploying a SCADA system. So ultimately, it evolved into an IEEE standard. We used to talk of DNP as being defined by either the Basic 4 or the Basic 8 document set. You'll hear that terminology pretty frequently. At this point, the official definition of DNP is contained in the IEEE 1815 standard, and pretty much anybody can get that from IEEE. You can download it and it act as a standard documentation for how the protocol is used. It is also available for download and for any ongoing technical issues that are being discussed from the DNP.org website. You do have to be a member, and that does require some contribution from your employer to be a member of the DNP users. But once you get on the DNP.org website, you can download all kinds of ongoing discussions about how the protocol is evolving into the future. There are, in fact, DNP I don't want to convey is the be-all, end-all of substation communications. One handicap that I would probably call people's attention to, although it's a perfectly practical protocol, is that DNP was conceived of during a time when communications, electronic communications, was all done by serial RS-232, RS-485, with baud rates ranging anywhere from 1,200 bits per second to 9,600 bits per second, and really pretty much no faster than that. In 2017, with the maturing of the internet and TCP/IP as a network conveyance for communications, protocols that were limited by the ability to put things into 16-bit integers and communicate at 9,600 baud, you can imagine that tools are available now to make communications more efficient. So DNP is mature. It's well accepted. Its compatibility issues have been resolved. I don't want to give the impression that this is as far as technology can take us in terms of SCADA communications. I don't want to make this into a promotional thing for IEC 61850, but there are protocols available for SCADA communications that are being hammered out in pilot projects throughout the United States and through the utility industry worldwide, like 61850, that don't suffer from the limitations of 9600 baud, 32 and 16-bit integer communications. And so you can imagine that DNP wants to keep pace with this technology, and it will evolve over the next 10, 15 years into something, you know, even more powerful. Conformance procedures and testing certification was established back in 2000. That means that if you really run into problems commissioning a piece of equipment or deploying a SCADA system and it looks like the compatibility simply can't be resolved, you can always go back to the certification testing and determine whether the device that you're trying to integrate is actually certified as DNP compatible, or if they have exceptions to the standard, and that would help to determine whether it's a good choice of equipment or not. So that's about it for the origin and development background. The basics of how substation communications operates is that the protocol defines basically a master station and an outstation. You can talk about clients and servers, talk about masters and slaves, but basically the functionality that is performed in substation communications is some variation of a master station, which is gathering information, and an outstation, which is providing the information that the master wants. Now, the way this is done is that the master and the outstation all maintain a database. The master station will probably have a much larger database, but the outstation basically is a subset of the master station's database. So during a poll response exchange, what you're basically doing is taking the database that's on the outstation and you are updating quantities that are maintained in real time with the database in the master station. For people who have a background in electronic communications, you'll frequently hear about the OSI 7-layer model. And I believe that it's beyond the scope of this presentation to go into great detail about the distinction between each of the different layers. But for people with that kind of a background, you want to categorize DNP as essentially being some people call it a 2-layer protocol, some people call it a 3-layer protocol, but basically you've got the data link layer and the application layer, and everything else is either understood or it's taken care of by the TCP/IP stack. So I'm not going to say very much about what distinguishes the different layers, but for people with that kind of a background, this is the only layers that are defined by the DNP standard. All right, so within the organization of a master station and an outstation, you can have a number of different ways to connect these devices together. Certainly what I'm showing on the screen doesn't require an awful lot of detailed explanation, but I would look at the top one, the one-to-one connection, as being more or less equivalent to an RS-232 connection, where you've got a single master pulsing a single outstation for remote data. Multi-drop would look similar to a RS-485 type connection. In this case, the master has an address. Each of the 3 outstations shown has its own unique address, and the master station basically sends the same data on the same wire to all 3 devices, but only the device that's addressed needs to respond. In the hierarchical structure, this would be more similar to a local data concentrator in a substation, let's say an RTU, where the master station holds RTUs in different substations, and each of the RTUs acts as a master for IEDs or meters or devices that are located throughout the substation. And then we get into more complex arrangements. Typically, because of the prevalence of proprietary protocols prior to DNP becoming sort of the de facto standard in the United States, you'll see some combination of substations that either have proprietary devices in the substation that have to be pulled by DNP, or more likely, you would very likely have a large financial investment in a SCADA master station. You could have a large financial investment in a master station using a proprietary protocol that you're still trying to, get your money's worth out of. But all of the devices, all the RTUs, all the meters, all the IEDs in the substation are now, for intercompatibility's sake, operating with DNP. So you need some type of communications converter to convert the database from communications in one protocol to communications in another protocol to bring the same database, the same content from one area to another. This is a place where the Orion can be very helpful. Okay, so implementation levels, you'll hear this, probably one of the first things you'll hear when you're talking about a meter or an IED or a relay is whether it's a level 1 device, a level 2 device. Typically, level 3, you're only talking about RTUs and SCADA masters. Things that actually pull other devices have to have level 3 compliance. But level 1 and level 2 really come down to different subsets of functionality that are supported by the outstation, by the meter, by the IED. The DNP protocol doesn't really give an awful lot of distinction between, what has to be a level 1 device, what has to be a level 2 device. There are a number of optional functions. So you can have a level 1 device that supports a number of functions in level 2, but doesn't support all of the level 2 functions, may be perfectly usable in a SCADA system. The only distinction that I want to draw in the context of this presentation is that a level 2 device typically has to support more of the functions defined by DNP than a level 1 device. You can think of a level 1 device as I go out and ask it, what's the volts, amps, watts, and bars right now? And if the device can respond, it's pretty much a level 1 device. There are other more sophisticated functions that would distinguish level 1 from level 2. Many of the IEDs available today are level 2 devices. That's pretty much what you should expect from an IED in a substation. What is this message structure and the functions that are supported by the protocol that might be used to distinguish a level 1 from a level 2 from a level 3 type device? So basically, in any hierarchy, you could have almost an infinite number of subcategorization. I want to start off saying, this is pretty much all there is. There's basically 5 levels of hierarchy in the message structure. And if you can distinguish group and variation from function and control codes and see the difference between all of that and internal indications, you will have a good idea of how the message structure in DNP is constructed. Starting with object group and variation, DNP is an object-oriented protocol. Now, in the modern 2017 sense, an object-oriented protocol, you might imagine the object would be amps. I want to know what the amps are. I ask for the amps, and amps means amps. Well, that's not really the way DNP works. Remember I said when DNP was conceived of, we were talking about limitations imposed by, point-to-point 9600 baud communications of integers. So the objects that are defined under DNP are numbered, and there's a definition in the standard of what each of the numbers represents. So the two major definitions, the two major components of the definition of an object in DNP protocol are the object group and variation. So you can imagine an object as being, let's say, object 60 variation 1 is probably the most common object that you will see an RTU issue a poll out to a number of outstations. But that's the way they would be referred to in normal speech. So object 60 variation 1, you can see from this table, is a class 0 poll. And this is what I mean by defined in the standard and understood by the users. So what's a class 0 poll? So an outstation or a meter or an IED will have basically a meter does kilowatt hours. A SCADA class instrument might do amps, volts, watts, and bars. A relay might have statuses and alarms and targets. But any of those devices has a limited number of objects that are available. And class 0 is basically a way of saying, I want to know what all of that is. Just, it's like the fast meter command. Tell me what you've got for me right now. You can see from the table here, there are different groups, not just object 60. And there are different variations that distinguish within a group what do I want to know about that general category. Without reading it to you, you can see some distinction between group 1, group 10, group 12. I'll call them to your attention. Group 10, group 20, and group 30 are respectively the way to get binary information counter information. Counter would be like kilowatt hours. It monotonically increments. It never goes up and down like amps do. So counters would be like kilowatt hours. And analogs, which do go up and down like volts and amps, that would be the way that an RTU could ask for just amps, volts, watts, and bars. Give me object 30. That would give me all of the analog values available from a panel instrument. Or object 20, give me all the counters from a billing meter. From a relay, give me all your binaries. But by grouping those together, when you have some combination of analogs, binaries, and counters in an instrument, you can group them into classes. And then the class 0 would be, well, I'm going to talk about static and event data here in a second, but basically your object 60 is the class data, which basically says for the class of device that you are, give me that data. Okay? I think I may have beaten this into the ground a little more than I need to, and what I've said so far does suggest a little more definition about things like static and event data. So I'm going to go ahead and move on to the next slide. I have a slide that talks about the difference between static and event data, and I'm not sure that it's adequately handled on this slide, but I'm going to talk about it right now. So static polling essentially means the master station would like to know what the value of all the measurements, whether they're binary, you know, is the breaker open or closed right now? What are the amps right now? What are the volts right now? What are the kilowatt hours delivered right now? That's static data. And you poll, the outstation gives you a response. That's what the data is right now. That might be of interest, but there is also recognition that doing that frequently enough to keep the master station updated in real time, 24 hours a day, 7 days a week, when you've got thousands of feeders throughout a distribution area, is a tremendous burden on bandwidth. So to use the bandwidth more efficiently, DNP defines type of poll called an event poll. And what the event poll does is it basically says, look, don't tell me what the data is right now. Tell me when something interesting happens. So if nothing, it's frequency. Frequency goes up and down, above 60, below 60. If it doesn't go more than a tenth of a hertz above 60 or a tenth of a hertz below 60, I really don't care that it's 60.004 or 60.003. But if it goes above 60.01 or 60.1, then I want to know about it. That's an event. The class 0 poll is a static poll. Class 1, 2, and 3 polls are event polls. So by defining in the outstation what amount of change constitutes an event, look at it this way. If it were a binary, like the status of a breaker, any change from a 0 to a 1 or a 1 to a 0 is an event. So that's easy. But with frequency, it might be a tenth of a hertz. It might be, 5/100ths of a hertz. You would define that subjectively based on the operating tolerances of your system. So when the event occurs, tell me about it. But if I give you a poll that says, I want to know your events and nothing has changed of any significance, then I don't need to use bandwidth to report that nothing interesting has happened since the last poll. Okay, so going down to the next level in the hierarchy, function codes and control codes. These are numeric codes. They're buried in the syntax of the poll and the response. And what they do is they further define what you want to do within that object that we already defined. So for example, to control a breaker or to set a bit, say you wanted to reset the energy on a meter down to 0, you have to send a control output. So object 12 variation 1 is the control relay output block. So that tells me I want to do a control, but it doesn't tell me, do I want to close this contact and leave it latched? Do I want to pulse the contact? Do I want to select before operate? Do I want to direct operate? All of those finer distinctions are made using function codes and control codes. Now, each of the different objects has different function codes and different control codes, which are specific to the object that you're addressing. So it's very easy to use object 12 variation 1, the control relay output block, as an example, but you could have function codes and control codes for analogs, for counters, and they would do things that are particular to those types of objects. So, for example, I'm showing you here how you would distinguish, function code 3 to select, function code 4 to operate in a select before operation of a breaker. But then if I want the operation to be a pulse, or if I want it to be a latch, I would use a control code. And as I say, I think it's beyond the scope of the presentation today to parse out the exact place within the message structure where the object type and the object variation and the function code and the control code go in the sequence of bits. But I think it's important to know the sort of macro structure of the command that control codes and function codes give you that level of selectivity within an object. Okay, so just to give you some examples of frequently used function codes, I'll give you a minute to look through this. You can imagine read and write would be the sort of function codes that might be pertinent to analog values like amps or kilowatt hours. If you just want to read a value, you can use function code 1. Select, operate, direct operate, freeze and clear. I think freeze and clear, frozen counters, when do you freeze, when do you clear, what's the difference between freezing and reading, is all pertinent in the context of reading billing meters with DNP. So essentially, suppose you've got 200 meters that you want to read. And if you're using a serial protocol and you read meter number 1, and then a few milliseconds later you read meter number 2, and then a few milliseconds later you read meter number 3, by the time you've got to meter number 200, so much time has gone by, the kilowatt hours have continued to run, you don't have an idea of what the reading of the register was across the entire population at the same moment in time. So the concept of freezing counters is pertinent to this, and there's a number of ways that you could deploy this. So you could, if the meter supports it, you could tell a meter, I want you to freeze counters every hour on the hour, and it would just basically take whatever the reading of the register is, and it would set aside that reading in a frozen counter that doesn't change, doesn't increment as the kilowatt hours go on, while the running counter continues to increment kilowatt hours. And then what the master station does is, instead of reading the running counter, it reads the frozen counter. So by reading the frozen counter, you have an entire hour to read your 200 meters instead of reading them sequentially. You can still read them sequentially, but the information that you get will all be what the kilowatt hours were at the top of the hour. Now, you can also deploy this as a command from the master station to the outstation. You could say, a broadcast command to all 200 meters at one time, freeze counters. And then what it would do is each meter would take their running counter, move it to a frozen counter, and you would have as long as you want to read the frozen counter. There's the command function code 10 you see near the bottom, freeze and clear. Function code 9, rather. 10 is just with no acknowledgement. Freeze and clear is a particular way of deploying a frozen counter, where the frozen counter basically records what the register value was when you sent the freeze and clear. And the next time you read it, after you do the freeze and clear, the next time you read it, it'll give you the amount of kilowatt hours that has transpired since the last freeze. So in other words, if I send out a freeze and clear every 15 minutes to a meter, I can get interval data, the 15-minute demand. So the kilowatt hours incremented in the last 15 minutes was this, instead of reading the running register, which tells you the total kilowatt hours since the meter was deployed. So all of those things are capable within, they're supported within DNP, and a good SCADA technician should be able to bring those kind of functions to bear, depending on what the objectives of the meter department are for doing periodic readings of their meters. Okay, so finally, at the lowest level of the hierarchy that we've defined is something called the internal indications, or the IIN bits. Now, where internal indications comes into play, is in a master-slave serial protocol, where the master initiates communication. All the slave can do is respond. It can't initiate communication independent of the other slaves because of the fear that communications would collide on a master-slave serial network. Not a problem with TCP/IP, by the way, because packetization. But on a master-slave network, if all of your slave devices can talk at the same time, there's nothing to keep the bits from colliding with each other and nothing but garbage coming back to the master. So because DNP was conceived of during a time when master-slave communication was, basically the state of the art, the IIN bit was invented, if you will, simply as a means for the outstation to communicate information that it once communicated to the master station without initiating independent communications. If that makes sense. So what happens is you're expecting the master station is polling maybe every 2 seconds. It could be polling for integrity polls, which basically means tell me everything that you've got right now, or it could be polling for event polls, where it just wants whatever is of interest that happened in the last 2 seconds. But when the outstation responds to the master, it has 2 words, IIN1 and IIN2, which are packed bits, and all of the bits will be 0 if there's no information that it wants to communicate. But if any one of those bits is set, which bit is set represents what information it wants to communicate to the master. So a very common use of IIN bits is need time. You see it here, IIN 1.4. So if a billing meter out in a substation is relying on the RTU for time sync, it may have a function built into it that every 15 minutes or every hour set the IIN 4 bit, and when the master station polls it and it receives the response telling it whatever the answer to its question is, the IIN bit, it will recognize that the IIN 4 bit is set. That means that that meter needs an update to its time sync. Then the next time the master station polls that meter, it will include a time sync signal. And it will only send a time sync signal when the outstation has set its IIN 4 bit saying, I need an update. Go ahead and update my clock. So this is a way that outstation can say, you can see the bits that I have listed on the table here. The device is in trouble. The device restarted since the last time you called me. The device is in local control. You can't reset my counters because the meter is in local control and it can only be controlled in the substation with a local keyboard command, for example. Things like that can be communicated to the master station using IIN, internal indication bits. I did mention there are 2 words, IIN1 and IIN2. So you can see on this slide I show some of the bits represented in the second word are. Things like buffer overflow or the configuration is corrupt. These are things that are probably less frequently necessary, but so they're in IIN2 instead of IIN1. But the idea being that there are enough bits to communicate anything that the outstation might need to say to the master during a regular polling sequence. So application, okay? This is the slide I was referring to earlier when I was tossing around static data and event data without having described it in enough detail. So we've already covered this. Static data is the present value of the data. So if I was to ask you a meter, I'm a master station, I'd say, what are you reading for, amps right now? What are you reading for frequency right now? You would tell me what the reading is. That's static data. Event data, I would come back and say, I know that we're regulating voltage on that bus, and I'm interested in knowing if the voltage has gone above this set point or below that set point so that I can tell somebody to throw in a capacitor to support the voltage, or I can tell somebody to do a tap change under load. So all I want to know is if the voltage is in those boundaries or not. Tell me if an event has occurred where the voltage is deviated from the boundaries I'm interested in. That's an event poll. Frozen static data, you can imagine, we've talked about frozen counters at this point. Basically, you've got the running counter, which updates in real time, and you've got the frozen counter, which basically is a snapshot of the rolling counter at the time that the freeze was ordered. And frozen event data is very handy because frozen event data, if events occur between polls, let's say you don't have a continuous communication with a particularly small unit substation, and you connect to that substation once an hour with a cellular modem that has to go out, dial a number, establish a connection, get information that's of interest, and then disconnect. So frozen event data gives DNP the ability to say, since the last hour when you connected last, here are the events that occurred, timestamped for when they occurred. And you can update your database and keep everything in perspective. Now, that could be, in a billing meter, that could be hourly kilowatt-hour data, but it could also be for operations. It could be, when did this breaker trip? Or how many times did it trip? Reclose and lockout cycle or something like that. So frozen event data is very helpful. And those are the sort of polling schemes. And then the data structure. Okay, so we've talked about how information is conveyed from the outstation to the master, but we didn't really say very much about the data itself. So the content has to be, stored in a certain way. Binary data is probably the simplest data to store. Obviously, in a binary protocol, 0 is, either off, low, open, or closed. You can define it as anything you like. For example, an A contact on a breaker could mean the breaker is open or closed. If you're looking at an A contact or a B contact, one of those bits being high could mean the breaker is open, or it could mean the breaker is closed. So there's no unique definition that a 0 is always open and a 1 is always closed. It's situational. It depends on the circumstances. And then just because of the possibility that the voltage could vary because of some lightning strike or some interference that you have no control over, can I rely on, if I see a single bit that represents whether this is open or closed, is that a good way to communicate binary data? There's also a definition called double point status. And if a device supports double point status, then it uses 2 bits to represent whether something is open, closed, high, low, true, false, whatever the case may be. So typically the best example of double point status is a motor-operated disconnect. So if you can imagine, a breaker operates almost instantaneously. It moves in a matter of milliseconds, microseconds for that matter. But a motor-operated disconnect is closed. There's current passing from the bus into a breaker. And then let's say you take the bus down for maintenance. You open the breaker. Boom, there's no current going through it. Now you have to open the motor-operated disconnect to de-energize the bus for maintenance. So the motor-operated disconnect has an A contact and a B contact. If the A contact is high, that means it's closed. If the B contact is high, that means it's open. But because a motor-operated disconnect might take anywhere from, a few seconds to a few minutes to travel its entire motion from fully closed to fully open, you could have a condition where both the A contact is low and the B contact is low, and that means that the disconnect is actually still in motion. And you would want to know that condition distinct from fully open or fully closed. And this gives you the ability with 2 bits to have 4 conditions defined. So if the A contact and the B contact are both open, it's moving. If one contact is closed and the other one is open, it is either fully open or fully closed. And if both the A contact and the B contact are closed, you've got an abnormal condition, which might mean, you need maintenance, or it might mean, something's broke. So, obviously double point status can give you more reliability, for more critical information. It can communicate a binary status with more reliability than a single point status. Analogs. So for analog data, like let's say you have 852 amps. How do I communicate 852 amps to an RTU from a panel meter or transducer or something like this? That's usually done in DNP, frankly, with a 16-bit signed integer. Now, with 16 bits, technically, from 16 zeros in a row to 16 ones in a row, you can count from 0 to 65,535. But because some values, like watts and vars, can be both positive and negative, I need a way to represent, with a 16-bit integer, positive numbers and negative numbers. So if you can imagine that the number has to be symmetrical about the 0 point, in other words, it can go as far negative as it can go positive, and you would like 0 to be 0, what we typically do with binary math is we make counting from 0 to 15 ones. Well, it'd be a 0 in the most significant digit, followed by 15 ones. is the largest positive number that I can count up to. And it turns out 2 to the 15th is 32,767. So what happens when the first bit is high? Well, that makes it a negative number. So from 32,768 to 65,535, those are all negative numbers. Now, we would have to get out a chalkboard and do a little bit of rigorous math to explain why binary math works this way. But it's a method called 2's complement, which I would commend to you for further study. And the basic idea is that if I take two 16-bit numbers, one of them negative and one of them positive, and I put one above the other on a chalkboard, and I add the bits, least significant bit, then the next bit, then the next bit, then the next bit. If these two numbers are equal in magnitude and opposite in sign, that should add to 0. Now, the way that works is you use this method where the most significant bit is essentially your negative sign. You take a number, let's say the number is 6. You basically invert every bit in the positive number, and then you add 1. So if you take every bit in the binary number for 6, you invert it, and every 0 is a 1, every 1 is a 0, and then you add 1 to the result, you get -6. And if you were to put +6 and -6, one above the other, and add them bit by bit, you would see that it would come out to 0. And that will work using 16-bit 2's complement. As a result, 32,767 is typically described as the highest number that you can represent, highest positive number that you can represent with a 16-bit 2's complement integer. As a result, when you define 100% of full scale in an analog way, for example, 5 amps on a CT, on the low side of a CT is 5 amps. Let's say the CT has a rating factor of 2. That means it'll read up to 10 amps with accuracy. We would say 10 amps is the full scale. And 10 amps on the secondary side of the CT represents 32,767 counts as an integer. Anything below 10, say 50% of 10 is 5 amps, would be 50% of 32,767. And that's the way the integer for 5 amps would be represented. How do I convert that into primary engineering units? You take the integer that you read from the meter or the panel meter or the IED or the relay. You take that number, you divide it by 32,768. That gives you a percent of full scale. Then you multiply by the definition of the full scale. In this case, we were talking about 10 amps. So 50% times 10 amps is 5 amps. And then you multiply by the CT ratio. CT ratio is published. It's in the drawings. Maybe it's 800 to 5. So 5 amps times 800 to 5 is 800 amps. And that's how you get your integer. If you ever go into an RTU and you see a number that appears to be out of range, and you read the number, and the number is like 72,156, it's not out of range, it's negative, because the number is greater than 32. I said 70, didn't I? Let's say it's 40,000. 40,000 is greater than 32,000, but it's less than 65,000, therefore it's a negative number. Sometimes RTUs can be set up to read a number as a 16-bit 2's complement number and not recognize that a number greater than 32,768 isn't out of range, it's just negative. That's a common error. We hear that sometimes from the guys commissioning the RTUs. And it's just something to look at, otherwise, you're going to scratch your head and say, where did this number come from? Obviously, there is some value in having values that never go negative, like kilowatt hours. Use all 16 bits. So if I can count up to 65,535, if I don't have to worry about reserving some portion of my full range for negative numbers, I can count up to 65,000 kilowatt hours. Or if I want to, 65,000 might represent 65,000 megawatt hours. And I can use all 16 bits as unsigned data. That would be a setting in the RTU. It would be a setting in the IED. It would be the way the information was coded. And then because kilowatt hours, basically can run and run and run and run, and the load on a transmission line or for a power plant could be enormous, you can actually, within the definition of DNP, you can assign a 32-bit unsigned data for counters like kilowatt hours on a power plant. And then it'll count up to basically 4 billion, almost 4,300,000,000 counts before it rolls over. So it gives you the ability to continue running that odometer in your car past 100,000 miles up until the actual life of the car, if you will. With a power plant, if you're measuring the output in megawatt hours, you might need 32-bit data to convey that information. Floating point is defined in DNP. It is defined in IEC 61850 and other more advanced protocols. But at the present time, because of the standardization, floating point data is very, very, very seldom used in the DNP context. There is a whole discipline to taking floating point data and putting it into binary representation so that it can be communicated. And I just think that for as often as that's used, it's out of the scope of this conversation. Okay, we've already talked about scaling in the terms of 32-bit signed, 16-bit 2's complement signed integer or signed analogs. So let me talk about a couple other scaling methods that you'll see pretty often in DNP. So for example, frequency. If I only need to know the frequency down to plus or minus 1/100th of a hertz, and 60 is, 6,000 is less than 32,000, there's no reason I can't represent 60 hertz as 6,000 counts, because it's never going to go up to 32,000. So 6,000 divided by 100 is 60, is your 60 hertz, and an increment in either direction, up or down, of 1 bit can represent a move of 1/100th of a hertz. So you just take the integer that you read from the IED, you divide by 100, you've got your frequency. That's one way to look at it. Suppose you need the frequency down to 1/1000th of a hertz. Well, using the method that we just described, you would have to be able to count up to 60,000, which you can't do with a 16-bit 2's complement number. So there's another type of method of scaling data where you say, okay, I know that I regulate my frequency around 60. So I'm going to assume the 60 part, and I'm only going to encode as a binary integer the deviation above or below 60. And then I can give you an integer in the meter that you divide by 1,000, and that will give me resolution, plus or minus 1/1000th of a hertz. So when I take the data, I have to take the integer from the IED, divide it by 1,000. That could be a positive or a negative number. And then I add that to 60, and that gives me my frequency with a resolution down 1/1000th of a hertz. That leads us into the idea of primary engineering units. And some relays and some meters, some panel meters, some IEDs will actually say, okay, if I'm not going to be reading in volts and amps, but I might be reading in kilowatts and megawatts, or kilovolts and megawatts, I can know that I'm never going to exceed 15, 16 kilovolts on this distribution line. I have 16,000 counts available to me in a 16-bit 2's complement number. I can count up to 16,000. I can represent the primary engineering units in binary number, and I never have to worry about going over range. Well, that's a perfectly good, legitimate method. Typically, you would be reading in kilovolts, so you would have to take the integer and divide by 1,000. Or you would be reading in megawatts, where you would take the integer and divide by 1,000,000. And then the representation that you get when you do that math is the primary engineering units. The advantage here isn't accuracy. It isn't resolution. As a matter of fact, you lose resolution, because you really can't do better with a 16-bit 2's complement number than, say, the biggest number that I have, 100% of my full scale, is 32,768. You get better resolution with a single count of the integer if you scale it that way. But really, if you're measuring amps, you don't need to measure amps down to a fraction of an amp. So if, reading in primary engineering units gives you sufficient resolution for the job you're doing, the advantage is to the person commissioning the RTU, that when he looks at a meter and it says there's 872 amps on this line, and he reads the DNP integer as 872, he doesn't have to do any math. He knows that it's working, and he can move on. It's a little more efficient for him. That's really the big advantage of primary engineering units. And it's really a question of whether the IED supports it or doesn't support it, and it's a question of a setting in the IED to make it conform to that. Okay, that essentially sums up the background, how DNP came to be, the object orientation and hierarchy of the commands, the message structure, and how different types of commands can be issued. And it says what the data is going to look like and how to interpret the data when you read information from an outstation, an IED, a meter, a relay, or whatever you like. At this point, that's the background information,